This is a continuation in a series of videos whose express purpose is to show you how to solve various kinematic problems of varying levels of difficulty effectively and quickly using the SUVAT method. Now, I'm assuming that you've seen the part 1 video, introductory video, so if you haven't, I would encourage you to do so. And in it, I have an outline here. In the introductory video, I explain the rationale behind the SUVAT method and also review general kinematic concepts and terminology, and also do equation derivations in details of the kinematic equations. So you can pause the video if you want to look at this outline in a little more detail of the first video. Okay, so let's get to, we're going to work 3 kinematic problems in this video, but before I do, I'd just like to do a little review of some of the things I mentioned in the introductory video. And one is how to recognize that you got a kinematic problem, that you're going to use the SUVAT method. The first thing I do is always look for some evidence of constant acceleration of the object or constant deceleration of the object. So you'll look for that. Once you establish that, then you're basically going to be looking for 3 out of 4 SUVAT unknowns, SUVAT variables that you need. So you'll be looking for initial and final velocities, displacement, or time. You need to find 3 of those. And then the 4th one is what your solution will be. So you're not concerned with forces acting on the objects. So no newtons will be involved. You're not concerned with mass, so no kilograms will be involved. And you're not concerned with energy, potential or kinetic energy of the object, so we won't be dealing with joules. And just to review the steps, it's 4 steps. You write SUVAT vertically. 1, 2, you enter 3 out of the 5 SUVAT variables next to their letter. Then you circle the variable that you need, your solution that you need, and then you draw an arrow through the variable that is left and use the equation that's affiliated with that variable to solve for the circle variable. So what you get right before you solve your answer is something that looks like that, and you will have this equation to fill in 3 out of the 4 unknowns of that equation. So basically, in each problem I'll show you this, so you'll see that throughout each of the problems here in the video. And basically what we have here is the SUVAT method is just a simple algorithm to direct you. It's a simple algorithm-like method that will direct you ultimately, quickly, to the equation that you need in each problem, which is usually the biggest headache in doing kinematic problems. Alright, so let's look at the first question. If an object is dropped from a height of 500 meters above the Earth, what is the object's velocity right before it hits the ground? So right that moment, right before it hits the ground and stops, we want to know what that velocity is. So that would be the final velocity. So let's just remind ourselves of what a free fall is. I didn't define that in the first video, so I want to especially do that here, because this is a free fall problem. So let's just look at what free fall is. According to physicists, they say that a free fall is a one-dimensional or a translational motion problem where the object is under the influence of gravity only. So we're not concerned with air resistance. And that's not mentioned in the problem, but we'll assume that air resistance is not a factor here. So this is a free fall definition. Now people often use the term free fall to just mean like dropping a ball out of the sky, or a skydiver is falling from an airplane. And really free fall problems can be more than just something like that example. If you have a rocket that goes straight up and comes straight down, that could be considered a free fall. Even if the object has an initial velocity going straight down, free fall, or an object that goes up at one level and comes straight down and hits the ground at another level, that's also a free fall type kinematic problem. And so all of these are under the only under the influence of g, which is the acceleration, the constant acceleration near the surface of the Earth for objects. And we just, in our problems, we'll just round it off to minus 10 meters per second squared. So we're basically dealing with this kind of gravitational field line picture where everything's equidistant and straight down, just like I drew here. Okay, now projectile motions are not freefall problems because they're not one-dimensional. You've got two dimensions here, and so we don't call those freefall, even though the only acceleration that these objects are under is gravity. Okay, so back up here, we do have a problem where we've got constant acceleration, so that's the first thing we want to do. And now we're looking for the 3 out of 5 variables that we need, the 3 out of the 4 variables that we need. So first step 1 we do is list SUVAT. Step 2 is fill in the 3 variables that we are given. Well, we are told that it's an object that's dropped, so it's got an initial velocity of 0 meters per second. We also know that the object is under acceleration of gravity, or g, so we've got minus 10 meters per second squared. And the other thing is that it's displaced. It's 500 meters above the Earth. So we know that it's going to drop that far. So that's going to be, we're going to say that's minus 500 meters. Remember, in SUVAT problems or kinematic problems in general, you got to be very careful with the signs. We've got velocities a vector, accelerations a vector, displacements a vector. So we always have to put the signs. They're usually just plus or minus in these problems. So I'm going to arbitrarily define my 0 point, my interface between positive and negative, is where I drop the ball. Anything above that going up would be positive, and anything below where I drop the ball, I'm going to call that negative direction. So I'm going to put negative 50 meters there. Okay, so step 3 is circle what we need. Well, we're looking for the object's final velocity right there. So we're looking for v, so I'm going to circle that. And then the fourth step is draw a line through the variable that's left. We know nothing about t, and we're going to use the equation that's affiliated with t. So that's going to be v squared is equal to u squared plus 2as. So let's just take a look at that here for a minute. So we're going to draw a line through that and use this equation that's affiliated with this letter, this missing variable t. So what is that telling us? Well, remember what we're looking for is we're trying to find v. Well, we have this, we have that, and we have that. And so we've got 3 out of the 4 variables in this equation, so we can solve for v. We certainly don't want to use the equation that we've circled, the circled v equation that's affiliated there, because v's not in it. Remember, this equation doesn't have the letter to the left of it. So we're solving for v. Well, v's not in there. So there's a big no to that. And then the other equations, because t is not in this equation, it's in the other equations, other 4 equations. So we've got not only t, but we've also got v in those equations. So we've got 2 variables that are unknown, so we can't use those other equations either. So I'm not going to do this every time, but I just wanted to show you how this 4-step method is basically like an algorithm. It basically just by circling and drawing arrows, you're essentially saying no to the other equations and saying yes to the only equation that you can use to solve this question. So let's just kind of speed things up here, and here's the math that's already been worked out. So we've got our 3 data points here that we know. We've got our equation. We're going to fill them in. Now, I like to fill them in as the equation in the pristine form of the equation. You could have well, this is already we've got it's equal to v, so we don't have to algebraically manipulate this around. So all we need to do is just plug and chug at this point. So that zero's out, and then when you do the math here, you end up with 10,000 meters squared, because we're multiplying meters times meters per second squared, so we get meters squared seconds squared, and that's v squared. So we want to solve for v, so we take the square root of both sides, and that gets rid of the square on v, so we've got that v, and it also gets rid of the m squared and the s squared. So now our units are left with meters per second. Now remember, when you take the square root of 9, for example, in actuality you get plus or minus 3. So here we get plus or minus 100 meters per second, and we're going to choose the minus because we already said that down from the 0 point is negative. So there's our answer, minus 100 meters per second. Now, of course, I told you that SUVAT is a quick method. I took a lot of time to go through this equation, this problem. But if I had not taken little segues here, this problem would have taken a very short period of time to do. Okay, so we're going to the next problem, and let's see what it is. All right, so we've got a car that accelerates at a constant rate from 0 to 25 meters per second over a distance of 25 meters. Approximately how long does it take the car to reach the velocity of 25 meters per second? First thing I do is look for evidence of constant acceleration or deceleration. Well, they told us that the car accelerates at a constant rate, so that's good. So I know I'm in business for a SUVAT problem because they're asking me about a solution that's kinematic. How long does it take the car to reach a velocity of 25 meters per second? And all this information is kinematic information. Kinematics, we're only dealing with SUVAT. Those are the variables. We're not dealing with newtons, joules, or mass. So we got a SUVAT problem. And now notice that they use distance. Distance is actually scalar. But we can say that the distance of 25 meters is also the displacement because they're taking the same path. So we're starting here at 0. It's at rest, and it's going in a straight line path. So our finish is here. So our initial position and final position is a straight line, and the path, the distance, the actual path, is also a straight line. So this is equal to s, and we know that we've got a 25 meter per second velocity at this finish point. And what are we looking for? How long? So we're looking for time. Okay, so we've got 3 out of the 4 unknowns. So let's pull up our little SUVAT. Step 1 is to write SUVAT vertically. Step 2 is to fill in the information. Well, we know that it's going 25 meters. It's displaced. And we'll call to the right, we'll call that positive, and to the left, we'll call negative. Generally, we use the signs that are on the number line. You don't have to, but if you do something differently, then be consistent by using plus and minus consistently within the problem. But we're going to use right as positive. Its initial velocity was 0 meters per second, started from rest, and the final velocity was 25 meters per second. And we want to know, so we've done, that's step 2. We've fill in the 3 variable points that we have information on. Step 3 is circle the thing that we need. We need to know how long it took for this event to happen. And the last thing is, 4th step, is we're left with the variable acceleration. So we draw a line through the variable that's left, and we are going to use the equation that's affiliated with that. In that case, it's going to be s, displacement, is equal to final velocity plus initial velocity divided by 2. So the average velocity times time. So we're going to use that, and So as you can see here, we circled time, we drew a line through this. Notice that acceleration, we don't have information on acceleration. We're looking for time. Well, there's time. It's in the equation. We have that, and we have that. So we just solve for t. Okay. Now, the previous problem, I kind of went over the rationale behind why it's no, 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 and no to these, and yes to that. So I'm not going to do that again. But if you study this, you can see that this is really the only equation, given 3 out of 5 variables, that we can use. And so we are directed to it. So let's just go ahead and look at the math there. So we'll take this problem and we put 25 meters there. We've got the displacement, we've got our final velocity, we've got our initial velocity, we're solving for t. Now if you wanted to rearrange this before you did that, that's fine, but I just do it this way. So we end up with 12.5 meters per second. Put your units in when you're doing this so you can see how they cancel out. I think that's important early on to see that. And so it also helps you know if you're doing the problem, it's writing the right equation down correctly, because everything should work out. So we end up with this times t. So we're going to divide 12.5 meters per second from both sides to solve for t. So we do that up here, which I didn't really show in the step. We're going to divide it on both sides, which is this. So we end up with 25 meters over 12.5 meters per second is equal to t. And so when you do the math, you end up with 2 seconds is equal to t. Now this right here is, unless you do a lot of math, m over s, and how these cancel out may not be very clear to you by the way it's written here. And so let me just take a brief period to show you how that happens. So what we're doing is, I just want to show you how all that cancels out and you end up with just seconds. So just want to remind you that when you have a fraction over a fraction, that what you do is you keep the top fraction the same and you invert the bottom fraction, and then you multiply 1/3 and then 8 times 2, and you get 3/16. Okay, so we're going to do the same thing with this problem, with this setup here at this point. And what I'm going to do is I'm going to turn 25 meters to a fraction like this. So it's going to be 25 over 1 meters on top. And then on the bottom, 12.5 meters per second, I'm going to write that as a fraction. So we've got a fraction over a fraction. And so again, just like we invert and multiply this, invert that, and then multiply, we're going to invert this. So we invert the second and meter. So seconds is now on top, meters is on the bottom here. And then, as you can see, after it's set up that way, the meters will cancel out, and you multiply 25 times 1 second and 1 times 12.5, so you end up with 25 seconds over 12 point, that's a number, 12.5, and that's how you only get seconds. Okay, so the answer then is 2 seconds to that. And then the last problem is, it's a problem from the Khan Academy. I mentioned in the introductory video that the Khan Academy people have just in the last less than last year have provided a new test prep section for the MCAT, the new MCAT that came out in April of 2015. And fortunately, the AAMC has agreed to review the material that the Khan Academy people have put together for all sections of the MCAT. So I like to use the physics questions from that, because a lot of you guys may be planning on taking the MCAT, so why not look at some of their physics questions. And so this is a kinematic question, and so it's hard to read, so I just retyped it here. Okay, so we've got a top fuel dragster car. Top fuel dragster cars accelerate from rest down a 1/4 mile track, which is 400 meters, in under 4 seconds. Assuming constant acceleration, what would the acceleration of a dragster be if it sped down a track in exactly 4 seconds? Okay, so we're dealing with all the information in this problem is SUVAT kind of information, and the most important thing, first we want to make sure that we're dealing with a constant deceleration or acceleration. Remember, in the first video I mentioned that SUVAT problems are really only applicable to objects that are under constant acceleration or deceleration. Okay, so let's fill in what we know here. We have displacement of 400 meters, and it's to the right, so we're going to say it's positive. The car accelerated from rest, so the initial velocity was 0 meters per second. The final velocity we don't know. The acceleration we don't know, and the time is 4 seconds. So step one was list the SUVAT letters vertically. Step 2 is what we just finished. Fill in the 3 bits of information that was given in the problem. Step 3 is to circle what you're looking for. Well, we're looking for acceleration, so we're going to circle that. And then step 4 is to draw a line through the variable that's left and use the equation that's affiliated with it. And in this case, the equation is displacement is equal to ut, initial velocity times time, plus 1/2 at squared. Okay, so we're going to do that. And as you can see here, just to give you an opportunity, if you haven't memorized these equations, we're looking for this. We didn't have that, and so this is directing us, yes, this is the equation. We've got that information. We've got u. We've got t's, the t. So we're looking for a. Okay. And let's go down here. And again, since we're solving for a, if you want to rearrange your equation so it's equal to a before you put in the data, that's fine. I just do it this way. So we've got s, or let me change that. We've got our 400 meters here. We've got our 0 there. We've got our 4 seconds there and there. So we end up with 8 seconds squared times a plus 0 equals 400 meters. And then we divide both sides by 8 seconds squared to isolate a. And we end up with this. And that's great because acceleration is meters per second squared. So this is pretty easy to see how the units work out well. And so we end up with 50 meters per second squared. And that is our answer. So I don't want to make this video too long like the introductory videos. So we are going to stop here. I'm going to continue in subsequent videos with a lot more translational SUVAT problems, and they'll in general they'll get more difficult after a while. And after I run through a series of those, then we'll move to two-dimensional. And okay, again, I didn't think I mentioned this at the beginning, but I just want to say, as you work with me through some of these sample problems, you may notice that a few of them can be worked by skipping some of the steps. You know, some of them that you may find that, but I would suggest that you practice the 4-step method so you can ingrain it in your mind. Then when you get to difficult problems where it's not obvious to skip the steps, and that will arise, the steps and the equations will be second nature to you. And so just consider working through some of these as practice, even though you might be able to notice the answers without doing the SUVAT method. Let's see what else I wanted to say before I concluded. Eventually, I'm going to eventually at the end of these video series talk about shortcuts, because a lot of times teachers will tell you about them for certain types of kinematic problems, but I really don't want to do that right now because I don't want to discourage you from practicing just doing the SUVAT method and just really getting used to doing it. So if I throw in shortcuts right now under certain type problems, then it shows you an easier, softer way, and I don't want to do that for right now. Okay, thanks for your time, and soon I'll have another video out with more kinematic problems. Bye-bye.